Best thing about the Deep Foundations Institute is the collection of engineers, contractors, material and equipment suppliers, and academics. And so bringing everybody together means the stuff that we get done is useful and is immediately applied and is not in some out there academic corner, or it's not promotional to one type versus the other. It's really a true collection of the best of this industry.
Membership of the DFI has many benefits. As I said, there's, for the younger members particularly, there's a wealth of knowledge within the DFI's archives, if you will. The magazines, the journals, the publications. We have this organization called One Mind that we subscribe to, where there are literally thousands of documents on all aspects of deep foundation construction, design, etc. So from that point of view, it's a very, very important resource that comes free with your membership.
Learning about technical advancements, again, seeing what projects people are up to and what solutions other engineering firms have come up with, and then the networking opportunities that we get at the in-person meetings like this conference.
I think the technical committees is just another great way to get involved in DFI. You meet a lot of people in the industry that are very influential and important. They make a lot of decisions that we live by in the industry. So when you participate in a committee like that, you can see firsthand how design and construction is kind of sculpted. So it's a lot of fun, and it's a worthwhile investment.
It's an organization basically that guides not only the principles of what transpires in the Deep Foundation Institute or industry, but also brings everybody together to discuss common problems and provide solutions.
Good evening, everyone. I welcome you all to DFI India Groundwork 2022 Webinar 6. Few instructions before we start the program. Recording of this webinar is prohibited. Participation certificate for student attendees will be emailed in approximately 2 weeks. Online webinar recording will be available on DFI of India YouTube channel in approximately 2 weeks' time. You can ask your question anytime during the presentation. You just need to go to the live Q&A field, type out your question and send. All the questions will be taken after the presentation during Q&A session. Now we start the webinar, and it is my pleasure to introduce today's session moderator, who is Dr. Sunil S. Basarkar. Mr. Basarkar is General Manager and Head Geotechnical Engineering Department at Afcons Infrastructure Limited, Mumbai. Dr. Basarkar has a total experience of about 18 years in the field and 16 years association in academia in area of geotechnical engineering. Dr. Basarkar has published more than 50 papers in various national and international conferences and reputed journals. He is a core committee member of DFI India. Dr. Basarkar is also a fellow of Institution of Engineers India, Indian Geotechnical Society, Institute of Bridge Engineering, and Dr. Basarkar also serves as an editor of DFI Journal USA. I welcome you, Dr. Basarkar, and I request you to kindly take the session forward.
Thank you very much, Pranav, for the kind words of introduction. I'll take on this session as a moderator, and it's actually a pride for me to take up this moderation of this session, because I'm associated with the introduction of continuous flight agar pile in India with a committee formed by DFI, and CFA, or continuous flight agar pile, or what will often be referred as agar cast in place pile. So we have already initiated in India, and it is with success that 8 number of piles were executed, and they had been load tested, and they had actually shown great promise to the Indian field condition. Much will be heard by our eminent speaker, Mr. Morgan NeSmith. So we'll be continuing this session with the introduction which I have made. There'll be a presentation by our expert speaker on Agar cast in place or CFA piles, Mr. Morgan NeSmith, followed by question and answer sessions. So in the process of the presentation, you can put up your queries and questions in the chat box. And at end of the presentation, we'll be taking up the question and answers, which will be dedicated for about 15 to 20 minutes. And then there'll be a closing remark. To introduce Mr. Morgan NeSmith, he's a director of engineering at Berkel company Contractors, and he has done bachelor's and master's in civil engineering at Georgia Tech and has over 25 years of experience in geotechnical contracting and consulting. He started his career with Foguro Engineers in Middle East and then continued over to the Netherlands and performing site investigations in the Europe, the North Sea, the West Africa, Azerbaijan, and the Arabian Sea. Since 2004, he is specialized in the design and installation of cast-in-place piles and ground improvement schemes for Berkel, his current company. So this includes the use of data acquisition system for pile design and quality control. He had been immediate past chair of a DFII ACIP committee, that is a continuous flight agar pile committee of DFI at USA, and also the DD pile. In 2017, he was presented with the DFI President's Award, and he's also a diplomat in Academy of Geoprofessionals. So very good to have an expert in the field of the CFA piles. Without taking much time, I pass on this platform to Mr. Morgan NeSmith to commence his presentation. Thanks a lot. Thank you very much.
Thank you very much, Sunil. I hope everyone can see my screen. It's a pleasure to be here. I've had the opportunity to work with DFI India in some of the developments of the CFA pile, and I'm very happy to be able to talk about the technology with you today. We are going to go through some things very quickly because we do have a limited amount of time, but I would be happy to answer any questions. I hope you have questions, and again, please feel free to put those in. We're going to talk a little bit. I know Sunil has already referenced that we use a couple of different terms, continuous flight auger pile technology and also an auger cast in place pile. And we're going to talk about why we use those different terms, the current equipment that's available and how it was developed, the range of areas where we use auger cast and CFA piles. We'll touch on some of the design methods, but that's way more information than we can probably get too deeply into today. And then performance tests, how we load test the piles for final design. And one of the most interesting things for me is how we can, in real time, while the piles are being drilled, monitor their installation with automatic monitoring systems and use that data. So the basics of either the auger cast or CFA pile are we have a stem that has a fully flighted auger and it augers the hole. So it creates a hole and excavates that soil to the ground surface. Grout or concrete is then pumped usually under pressure to the bottom of the hole through the hollow stem of the auger, and there's a head of grout or concrete built up, and then we continue placing that concrete or grout as we withdraw the tool from the hole, leaving the concrete or grout pile. So the terminology that we talked about, all of these are cast in place piles. They're also all what we call single pass systems. That means we drill down one time and we withdraw the tool one time. And that's a little bit different from, say, a drilled shaft or a caisson where you may auger a little bit of the hole and then take out the material, put some casing in and continue on. And you have to auger and withdraw the tool multiple times. And these are all also rotary processes. So we're rotating a tool into the ground. So we do use the term CFA because both of these tools use a continuous flight auger. Now, in North America, we generally have called these piles auger cast in place or auger cast. when they were developed in Europe, they were using some different types of piles, and they had the hydraulic rigs that I think you're probably more familiar with in India. And when they adopted that continuous flight auger technology, especially in the United Kingdom, they were referred to these piles as CFA. And so that's kind of where the two terminologies developed from the 1950s and 1960s. There are a couple of other types of piles that are sort of related, but we're not going to get into those today. And again, from North America, we generally refer to, at least within the DFI in the industry, we refer to these as augered cast in place piles, but we do also use the term CFA as well. And I'll talk about a little bit about when we use the two different terms. This is a picture from the original patent, and this was from 1959 for the first auger pressure grouted pile, which was just the previous version of what we now call the auger cast pile. And here we have a solid stem that drilled and excavated a hole, and a casing was driven by right next to the auger, and grout was pumped into the hole as the auger was withdrawn. And it was in the mid 1960s that they were able to develop hollow stem augers, so we could get rid of this casing and pump grout or concrete through the hollow stem of the auger. So this is what, if you were in North America, you would typically see as a rig. We would have a crane, a crawler crane. And one of the reasons this is so common is because we have an abundance of crawler cranes in the United States. So it's very easy to fit these with the equipment for auger cast piles. So in this case, we have a set of swinging leads suspended from the crane. And then we have the rotary tool that travels up and down the leads, and that rotates the tool into the ground. And you can see a set of leads and the auger attached to the set of swinging leads that's suspended from this crane. What we started calling CFA, or what the UK has always sort of referred to as CFA, is the same technology, but installed with what we call a fixed mast or hydraulic rig. And these are dedicated drilling rigs, and you can use them for different pile types, but they're very common for CFA piles. And here we have, instead of the mast here being suspended from the crane, it's actually rigidly attached to the body of the installation platform. And then the rotary gearbox travels up and down the mast similarly. So they're very similar processes, but it's a difference in installation platform, where we use the term CFA for these hydraulic dedicated drilling rigs, and we use the term auger cast pile or ASIP pile for the crane supported systems. One of the flexibilities is you can design these augers with a range of angles and distances between auger flights. So generally there's about 75 or 76 millimeters inside the diameter. That increases a lot of times with large diameter CFA piles to allow more grout or concrete to be placed depending on the size of the pile. So overall, auger diameters for the crane mounted systems range from relatively small, about 300 millimeters, up to over 1200 millimeters. And there is at least a rig or a piece of equipment that is saying they can go up to 1500 or so millimeters diameter for CFA. But as far as I know, in North America, we've only installed up to 1220 millimeters, even with the CFA. So roughly about 4 feet is our limit. And we also can have a range of auger section lengths depending on how deep you're drilling. If you're drilling in areas where you have limited access, you can use shorter section lengths, but you can also use longer section lengths to drill very deep depths. And we have a range of drill bits that we can apply. We have our very basic bit here, and then a basic rock bit, which has teeth, you can see, as opposed to sort of scoopers for basic sandy soils. And then we have also clay bits for clayey soils to help excavate those as well. And you can see the difference between the flat blade and the pointed teeth, which we generally use for usually sedimentary rocks, shale, claystone, sandstone. Anything harder than that, like a limestone or granite, we're not going to be able to penetrate typically, even with these rock bits. So for the crane mounted system, again, we have a set of swinging leads supported from the crane, and we have to resist the torque that's being generated by the rotation of the tool at the top. And that's either done with a torque arm from the swinging leads back to either the boom of the crane, or very often these days for safety reasons, that's to the body of the crane, so that we're not structurally doing anything with the boom of the crane. And with the fixed mass platforms, you generally don't need that, because all of the resistance is provided by the rigid attachment of the rotating tool to the body of the drilling platform. As we drill longer and longer lengths, we can have a little bit of problem with bending or buckling of slender tools if the auger is too long. So we use intermediate auger guides. Generally anything over about, let's say 13 to 15 meters in length. When we're drilling any deeper than that, we'll generally start to use one or more auger guides. And again, we often don't use those with the CFA rigs, again, because they are rigidly attached and have slightly stiffer tools because of the higher torque that's provided by these rigs, and then have less chance really for buckling typically. So they don't often use the intermediate auger guide. One of the safety features that we always try to incorporate is an auger cleaner, and that's for either type of system, CFA or auger cast. And that's really to clean the soil off the spoils off the auger flights as the tool is coming out of the ground. We don't want that to go up into the air and then fall and potentially hurt someone. It sounds kind of funny, it's just soil, but if it's falling from a relatively high distance, it can do some damage to you if it hits you. So that's why we try to prevent that by cleaning the soils off the auger flights as we withdraw them. So our gearboxes, and these can be, again, this is fairly similar to what's rigidly attached to the CFA rig or to the swinging leads for the auger cast pile. Those are all hydraulically operated typically, and that's what travels up and down the leads. So the tool itself is not actually attached to the leads, it's attached to this gearbox, and the gearbox is what travels up and down the leads. And torques generally range from relatively low for small diameter piles to, we have equipment now that have relatively high torques, and we can put in, again, those relatively large diameters, where we're starting to see these piles replace smaller drilled shafts in a lot of the area of North America. For crowd, or that's the downward force that we're able to put on the tooling itself. For the crane mounted systems, that's the weight of the tool. So it's the weight of this gearbox and the auger, and that can be anywhere from about 10 to 45 kilonewtons, depending on the size of the tool and the diameter of the tool. With the CFA rigs, because they're rigidly attached, we do have additional crowd force that can be applied directly from the machine to the tooling besides just the weight of the tooling. And generally either system, we're going to rotate between 30 to 60 RPMs, and generally it's closer to 40 to 45, but we can slow down in some geologies if we need to, and in some very soft geologies we can rotate very quickly and advance the tool very quickly when we would like to do that. Again, these are generally hydraulic powered systems. And for the crane mounted systems, we have hydraulic power units that are attached to the back of the crawler crane. And with the CFA systems, those are built into the rigs that we showed you. And the horsepower ratings are relatively similar either for auger cast or CFA. Again, a range depending on the size of the tool, the diameter, and the length of pile that you want to install. So with either system, we generally use grout or concrete, and that's delivered either batched on site or most often in North America delivered by a ready mix concrete truck. So it's batched at a plant and delivered to the site. It's poured into the hopper here, and this is a hydraulically operated pump that has pumps under pressure here at about 2400 kPa at the outlet. Now, I do want to say that we're not really pressure grouting with this system. This high pressure that we're generating here is really to overcome these, very long grout hoses. We pump the grout or concrete for long distances, and then to get it up to the top of the tooling to go down the hollow stem, we need a lot of pressure. So I don't want to cause any confusion and say these piles are pumped under pressure when they're in the ground, but we do pump them under high pressures, again, to pump them over very long distances to wherever the crane may be. What that allows us to do is keep this pump maybe in one place that's very accessible for the trucks that are bringing the grout to the site, and then move the rig around without having to relocate this grout pump whenever we change piles. This has been a developing technology in the US for about 50 years, actually 60 years. I'd say it's relatively mature across most of the country, and we have some major facilities that are supported on AugerCast or CFA piles here in the US. I happen to live in Atlanta, Georgia, and so the world's busiest airport is here in Atlanta, Georgia. It's Hartsfield International, and that is supported here. You can see the AugerCast piles supporting one of the columns in Concourse E, which was the old international concourse at this airport. A stadium that has just been built in 2017 here in Atlanta is also supported on AugerCast piles that were around anywhere from, let's say, about 12 to 13 meters deep on the north side of the site to well over 30 meters deep. They were all drilled down to bedrock refusal, and that bedrock sloped again from about 13 to 30 meters from the north to the south of the site. That's one of the advantages of the system, is that we can tailor the length of the pile to meet variable conditions on the job site relatively easily. We can also put in very, very long piles. So this was with a crane mounted system. And these piles were, and I have forgotten to change my units, so these are probably about 40 meters, 45 meters maybe deep. And they were relatively large diameter piles that replaced the original drilled shafts that were intended for the project. This is one of the longer piles that's been installed in the United States. And that's something that we can do with the crane mounted systems. One of the things with the hydraulic rig systems, even the largest drill rigs that are available have a little bit less limited stroke of about 40 meters total drill length. But as far as the range of geologies, one of the great things about the system is it's very, very flexible in terms of the geologies that we can put these piles in. This is a project that was in the northeastern United States, right next to a river, and we see a sandy crust in the upper 3 meters or so, and then about 15 meters of very, very soft alluvial deposits, and then a little bit of sand overlying the underlying bedrock. And we installed AugerCast piles here and pumped. The important thing here is to just continue to pull the tool at a steady rate and not resist the temptation maybe to pump too much grout in this very soft soil. And so to continue pumping steadily and pulling steadily to the top of the hole. And then we actually find that we can very successfully pump AugerCast or CFA piles in this geology. Conversely, here in Atlanta, we have residual soils from an underlying granite that can be anywhere from the granite can be at the ground surface, or it can be 150 or more feet deep. So generally we have residual soils that are getting denser with depth. And then what we have is locally, we refer to this as partially weathered rock. It's what we call an intermediate geomaterial. It's weathered from the underlying bedrock, but it is drillable. And it's very, very stiff and gives us very, very high shaft resistances for our piles. And then we have the underlying bedrock. So in a boring or a stratigraphy like this, we would drill through the residual soil, and even now these days through all of this partially weathered rock down to the underlying bedrock. And what that's allowed us to do is really maximize the loads that we can put on these piles. We're really looking at structural limits of the concrete or grout that we're using as opposed to geotechnical limits because of the stratigraphy that we're installing in. So we can install these piles in very, very dense strata, even some, again, sedimentary rocks like sandstones and shales, but we can also install the piles in some very soft stratigraphies. This is probably for the future development, but one of the other flexibilities of the system is you can use them also very similarly to a micropile, where if you have limited access systems, there are pieces of equipment that we can use to install smaller CFA piles using dedicated pieces of smaller equipment, where we'll drill one section of auger down at a time, disconnect, and then use something like an auger handler to place another piece of auger. So it will still be one drill down and one withdrawal, but it will be done in sections. So it's a little bit of a slower process, but it does give you some flexibility in areas where there are existing buildings or for some reason there's limited access. So these are typical design limits, and in the US, we use, I don't know why we call it the International Building Code. I think we only use it in the US, but that's okay. We are limited to 30% of the unconfined compressive strength of the grout or concrete that makes the pile. So for example, if we have a certain, maybe on the lower side of what we have available in the US for grout or concrete, we might have design loads in this range for certain diameters. And that might be, say, for a soil. We would be limited by the geotechnical capacity of the pile and the soil. So we might not worry too much about the structural capacity of the pile. However, if we are in situations like where I showed with the partially weathered rock or drilling down to bedrock, we can use higher strength grout, and for some of those same diameters or even some larger diameters, put much higher loads on the same diameter pile by using the higher grout strength. So that will be a case of locally, as standards in India develop, what sort of grout or concrete strengths are available will be one of the limits that you'll want to keep in mind in terms of what the loads per pile that you install. And the last thing we'll talk about with the differences in the system, though, are one of the reasons we do use the crane mounted systems is we don't have a lot of fixed mast platforms in the United States, relatively speaking. There are a good number, but these really only started to appear in the United States in the 1990s and early 2000s. Some drill shaft contractors have some, but they're not quite set up to be flexible enough to use CFA technology. So that's one of the reasons the crane mounted systems are popular in the United States, is we do have an abundance of crawler cranes, and there is some flexibility in the system where we can sit the crane in one spot and move the tool as we need to. One of the things that Sunil and I were talking about before we started was that there really are an abundance of hydraulic driven rigs in India. And that's why one of the reasons we're starting to see these hydraulic rigs being used more and more in the US, particularly as we use larger diameter CFA piles to replace drilled shafts. But when we do use these, we do have to remember that we do have to drive up to every pile location. It doesn't have quite the same flexibility. It's just something we need to keep in mind when we're sequencing the installation, that we may need to start from one side of the site and work because we're not going to be able to reach back into some already constructed piles and put another pile in if we need to. So with either pile type, the materials are basically the same. We're using ready mix grout or concrete, and that's typically a cement, fly ash, but fly ash, I think in the future is going to be used less and less for some environmental reasons. And then for grout, we generally use just a sand, but for concrete, we'll use sand and gravel, and then water. And then there are a variety of aids that we can put in the pile to keep it in a fluid state so we can pump it, or do things like keep the water retention rate to a more appropriate level so that we can put reinforcing steel in the pile after we pump it. So we have a lot of additives that we use these days to keep the without reducing the grout strength to allow the grout or concrete to stay in a fluid state so that, again, we can place it and put reinforcing steel in. Generally, we use cubes for grout when testing the unconfined compressive strength. And then we use cylinders for concrete because of the aggregate size. But one of the things to remember is when you're looking at the unconfined compressive strength is if we test on the cylinders, and the cylinders generally have a length of 2 times the cylinder diameter, you're going to get lower results always with the cylinders than you'll get with the cubes. So you just want to make sure when you're specifying a certain strength, you know how you're going to be testing it and adjust. If you're saying you want a certain strength, but that's referencing a grout cube spec, and you're actually going to be using concrete, you want to make sure that you reduce your requirement because you're only going to get about 85% of the unconfined compressive strength by testing a cylinder. So one of the reasons we use that fluid grout, I did say it's not really under high pressure, but there is some pressure, and as we build that grout pile, there is a head of pressure. It's like any fluid column. The longer or the taller that column is, there is some pressure that can help expand the soil a little bit. But one of the best benefits is that fluid grout and concrete can really, once it's under the column pressure, it can really expand and fill in any of the small crevices that are created in the side of the hole. It won't be perfectly smooth, which is actually very good because it creates a very high shaft resistance with that grout or concrete to soil bond. But because it's heavier than generally the soil or either the hydrostatic or the effective vertical stress, that concrete or grout column stays stable. And that's why we don't have to use any casing. And we're able to drill one time down, pump the grout column or concrete column and just leave it. And it will stay open to allow it to cure or for us to put reinforcing steel in. And this is just an example of once we've pumped the pile and removed the tool, we do a little bit of cleaning at the ground surface. This is, again, manual cleaning of the top of the pile. And then we generally put in something to protect just, again, the top of the pile, where we use this particular tool has a hinge here so that when you dip it down, it folds up and goes through the grout. And then when you pull it back out of the ground, these flaps come open and trap any soil inclusions that are right at the top of the pile. And that's generally how we construct the top of the pile. Where we construct the top of the pile can be a little bit tricky with this fluid grout. Since it is in a fluid state, we generally don't use particularly deep cans. So if you're working from a particular ground surface and your top of pile is very, very deep below, there's going to be an excavation, for example, for a basement. You may end up wanting to place the top of the pile to about the existing ground surface, and then that pile will have to be cut down as that excavation commences. And one of the reasons is, particularly in areas where there's a high water table, the more you dip that grout column down, now we're taking away some of that fluid pressure that stabilizes the hole. And again, especially with a high groundwater table, it can want to come under that stabilizing can at the ground surface and bring soil inclusions into the top of the pile. And we want to avoid that. So oftentimes, even though it's a little more trouble in the final construction, we want to leave the piles maybe higher than they need to be for final construction and let them set and then chip them down during the final excavation. We have a range of reinforcement that we can put in. Center bars are typically used for tension resistance, at least in North America. And then we only use cages when we have lateral loads that need to be resisted, because grout is great in compression, but not so great in flex. So we want to give it some additional flexural strength with cages. We can put combinations in. If we have very high lateral loads, we can even put pipes in, steel pipes. And we have a variety of centralizers that we can put, again, on the piles. One of the things that I always try to say is, or I try to tell designers, is we don't want to try to shove too much steel into the pile. That becomes a little bit difficult, even if we have fluid concrete or grout. So it's often better to use a slightly larger pile to accommodate steel than to try to put a really high amount of steel in if you have very high lateral or seismic loads. And this is just an example of the steel being lowered into the fluid grout column once it's been placed, and then the steel sticking up out of the fluid grout column. And this is an example of the centralizers. We have what we call flywheels that we can put on cages, or also sleds, but those are all to keep the cages centralized. And we have similar things that we can put on the center bars, centralizers, or as we often call them, footballs, but that's American football, not international football, just because of the oval shape of the little attachment to keep it centered in the pile. All right, so capacity, or how are we going to design the piles? So for fine grained soils, the general rough method is generally the alpha method, which is an undrained shear strength method of designing shaft resistance and toe resistance. So from a design standpoint, we're either looking for undrained shear strength, or there are methods that have correlated cone tip resistance values directly, instead of having to go from QC to shear strength and then to capacity. Indirect correlations, if you can't measure the shear strength directly, you can estimate from SPT values in clays, Atterberg limits, and then there are also pressure meter and dilatometer tests that you can get undrained shear strength from as well. And the basics are, I think most of you are aware of this, it's similar for almost any pile design. The shaft resistance is equal to some alpha value times that undrained shear strength. And then the toe resistance is that undrained shear strength, again, times some bearing capacity factor. The primary recommended method in the US or North America was from the Federal Highway Administration, but this is the same method. It uses the same alpha factors for CFA piles as it does for drilled shafts. It's pretty good, but what I have found is there is a newer method from Coleman and Arcement. These alpha values were directly developed from augercast and CFA piles. So this relationship with alpha, it gives you slightly higher alpha values. And that's, I find, to be more realistic than these drilled shaft alpha values, because we do find that we get higher shaft resistance from augercast and CFA piles than we do with drilled shafts. And one other thing about shaft resistance is we have some various materials in the US where we found that they just behave a little bit differently. And that's what I would encourage you as a society, and in the Indian Geotechnical Society and the DFI India, to think about, is as you start installing these piles in various geologies, to maybe look at local differences, because that's what I've seen over the last 20 years is really there are some variations over the United States in different areas where, for example, in Texas, and we have over consolidated clays from desiccation where the water table has risen and lowered repeatedly over thousands and thousands of years, millions of years. We generally use a very, very high alpha factor, higher than either Coleman or Arcement or the FHWA method would tell us. So I know if I'm doing piles in certain parts of Texas that I want to use a much higher alpha factor. And that's one of those things, again, I would encourage y'all to just sort of pay attention to and develop maybe some local variations to overall standards. The toe resistances and fine grained materials, again, is fairly straightforward. It's just your typical bearing capacity factor. And I find for most piles that are in clay, this is fine. We generally get a combination of friction and toe resistance in these piles, but by and large, the shaft resistance plays a much larger role than maybe the ultimate toe resistance, unless you're in a very, very hard, heavily over consolidated clay, like some of these Texas clays. So this, I think, gets you close enough to the toe resistance that you're actually going to see in the field. Again, how do we get shear strength? Hopefully we can measure it directly. In situ is my favorite. If we have to do it in the laboratory, that's fine. We just need to be a little bit careful. We get in the US, and I'm sure around the world, we get a lot of standard penetration test results. They're not great for correlation, but if you have a lot of them, you could probably get a general idea of the shear strength profile. You just may need to be a little bit conservative in your design methodology because those SBT values are so related to the operator and how the tests are run, and they're very, very operator dependent. So we need to be a little bit careful in using those values. Again, I mentioned a direct CPT method, and I actually like to use this method when we can perform CPTs in certain geologies. This is either called the LPC or LCPC method. It was originally developed in 1982, but it's been updated. And it's been updated for a range of pile types. So for CFA piles in particular, there is a maximum side shear, but it's a direct correlation between tip resistance QC and the side shear. And then there is also a direct correlation between the toe resistance of the pile and the tip resistance from the cone penetration test. So it's a very easy method to apply if you do have CPT results. I find that it's just a little bit conservative, although it's gotten better as it's been modified over the years. And one of the reasons is when correlating some of the old load tests, maybe we didn't always test piles to failure. Sometimes they were just tested to twice the design load. And that was called the ultimate load, whether the pile actually failed or not. So I think our database has improved over the last couple of decades, and that has improved this direct correlation method as well. But it's still just, I would say, just a little bit conservative. So in sands, the big difference is we generally use drained design methods or beta methods, or again, we can have some direct relationships with cone penetration tests. So in general, again, this is the same equation you're going to see for any typical shaft resistance for piles. You're just going to vary some of these parameters depending on pile type. So in this case, we're coming up with a value beta times the effective vertical stress to come up with shaft resistance. And again, the most basic but generally recognized method to get you sort of started, but I think it's very conservative, is that federal highway method that gives you a range of beta values directly related to your effective vertical stress. And then there have been a couple of other databases developed in the last 20 years or so that can give you different methods or different values for beta that might be a little bit more applicable. What I find, again, I think I would encourage the collection of data and maybe the development, starting with these existing databases, but maybe developing your own local databases, because I do think these are all pretty good, but depending on where you are, this, I believe, is always going to be somewhat conservative, and it's going to depend on where you are geologically and how those sands are. Are they alluvial? Are they coastal? To which method is going to give you the best answer? They will all get you pretty close, and you know, you're going to run a load test typically to verify the capacity, but I really would encourage you to collect data on your own and develop local standards. Coleman and Arcement have also developed beta values that are actually pretty good, again, developed directly from CFA piles. And those are, again, a little bit better than the FHWA method beta values, since those were developed for drilled shafts and then applied to CFA piles. And again, generally from the in-bearing component, there is general agreement that you can directly from the in values from an SBT get toe resistances, and that works reasonably well. And they all sort of tend to end up at about the same place. So generally using the FHWA, again, for tow resistance in sand. If you're in a very sandy soil, you're by far, the pile resistance is going to be mostly in the shaft anyway. So I think this will get you a good enough estimation of tow resistance for design. However, in particular for sandy soils, I find that the direct method is very, very useful. The LCPC method, using tip resistance directly to get both side shear and tow resistance. We get some of our best estimations of capacity from CPT values directly. And in fact, I have internally within Berkel even gone so far as to taking our SPTs when that's all we have and correlating that to estimated CPTs just so I can use this method as a check. So I'm starting to use SPT values directly as opposed to going to some beta value for side shear. It's these direct methods for sands I find to be very, very accurate in terms of their estimation of capacity. One of the other items that you're going to want to pay attention to the more you start to use these piles, though, are local conditions. So we have in the southeastern part of the United States, for example, we have limestone, and technically, yes, it is a limestone, but it is not a very hard limestone. It's a calcareous limestone. Really, it's a hard cemented sand. So it's not like a dolomite or a basalt. It's not that hard. It's very drillable. And for those geomaterials, they don't really behave like a sand or a clay. So those design methodologies really don't apply. And that's where if you find, I think any sort of cemented or intermediate geomaterials that are sort of stiffer than soils for whatever reason, they've been heavily over consolidated or they've been lightly cemented, you're going to want to develop a local database, as they have here, for example, in these limestones we find in the coastal southeastern United States. One other thing that I will say, and I want to be very careful with this, is if you use the Federal Highway Micropile Guidelines, there is a document that's available free. And if we take a continuous flight auger, that is very similar to a type A micropile where the grout is just placed not under pressure, but under gravity. And so if you're looking at some rocks, especially soft shales, and you notice the design methods I gave for clays and sands in general. So if you are drilling into some softer rocks, you may want to look at these type A values for nominal, that's ultimate bond strengths between the grout and the rock. I find it works pretty well for shales and sandstones when we drill into those types of materials. I generally have started on the lower end of these values, but I'm finding more and more that when we're actually doing the load tests, we're getting closer to the mid-range to higher end of these values. But I would probably start a little bit conservatively when using them, but I think there's a lot of potential there for drilling these piles in soft rocks and getting high capacities. All right, so load tests. How do we test the piles? The most common load test you're going to run is for a compression test. We want to keep a building from sinking into the ground or just collapsing entirely. So we want to make sure the piles can support the compression loads from the structure that we're building. We have in the US at least decided as an industry that there's not a whole lot always to be gained by running very long tests. What we like to do is run the quick test, which has a lot of loading points. So we're loading in very small increments, but at a relatively high rate. So every 5 or 10 minutes, we are increasing the load. That's now so common that it's option A of this ASTM standard for compression loads. So the most common setup that you're going to see are either using reaction piles, or very common also to see a platform with a lot of weight, often concrete, precast concrete piles or other weight that supplies the load that we can push off of to test, to apply load to this pile. So we generally have a hydraulic jack and gauge and a load cell, and then dial gauges, and we'll apply load in increments and monitor the deflection of the pile head as we apply that load. One of the things I'd like to encourage is the use of strain gauges. We find that we call these sister bar mounted strain gauges because the rebar can be attached directly to the center bar that's inserted into a test pile. And they're very, very robust. So these are vibrating wire strain gauges that have wires coming up all the way out of the grouted pile, and you can place those at various lengths along your pile. There are other types of gauges. These don't have the sister bar attachments, so they have to be a little bit more carefully mounted to the pile. But using strain gauges of some sort will allow you to really get a hold of what's the different shaft resistances and the different layers along the pile, as opposed to just getting an overall view of maybe the average shaft resistance of a very long pile. So the other comments I'd like to make about load testing are, once we do get a nice curve with a lot of load points, maybe using that quick compression test method, we do want to try to test to failure when possible. We don't want to just stop, even though we use a factor of safety of 2 most often in the US when we do test piles. So let's say we test a pile and the design compression load is 100 tons. I think we used to, maybe 20 years ago, test to 200 tons, and that was it. That was all we would do. We are seeing as an industry more and more testing to really pushing those piles to an actual geotechnical failure if we can, or extrapolating the load displacement relationship so that we can get a better estimation of the actual capacity of the pile, as opposed to just saying, oh, that's 2 times the design load, that's it, that's where we're going to stop, and we're going to call that the capacity. So if you do get into methods of interpretation for ultimate load, and you happen to look at the International Building Code, it provides 3 methods for interpreting ultimate load. And the only thing I would say is this Davison method was developed for precast concrete piles, and you really shouldn't use it without a modifier of, I don't like to use it necessarily at all. There was a paper that was funded by the DFI specifically for auger cast piles that recommended using the Butler-Hoy method when you can get this type of extrapolation. But there are methods out there to make adjustments. Dr. Davison and in a more recent paper recommend a modified Davison method, and at least that gets closer. And that's using a modifier of 4 in this offset. So with the Davison method offset, again, there's the elastic line of the pile, and then there's some offset, but it's modifying and multiplying that offset by about 4 to use for CFA piles to get a better estimation of the ultimate load. And you can see here, again, we're getting about 350 tons and 360 tons, relatively close. Whereas if we just use the traditional Davison method, we would be really not allowing ourselves to use as much of the pile capacity as we actually have. Some of the other tests that you may start to see, and as we put more and more load are starting to be more common, this is a dynamic load test. So this is a test frame over, this happens to be a steel pile, but you could do this on a CFA pile. And so there's a weight, and that weight is lifted up to a drop height and then dropped onto the pile. And then the pile is instrumented so that it measures wave speed down the pile and back and correlates that to pile resistance. This weight is then dropped from various heights. And that's what we see here is the resulting estimated load at each drop height. So it's not a case of where you can directly measure capacity. It's a case where you run a series of tests and can sort of interpret an estimated CFA pile capacity. This was also developed for driven piles, and that makes a lot of sense, right? If you drive a pile and then you come and drop a hammer on it, that's kind of the same method that you were using to install the pile anyway. But that's not how we install CFA piles. Those are drilled and grouted. So I find we have to be very careful in using dynamic load tests in soil, but for CFA piles. But for piles that are installed to bedrock or refusal, they're very, very useful. They do, because the toe resistance we get with CFA piles on rock mobilizes almost immediately. We do tend to get very good results with dynamic load tests, correlating them with static load tests. They're very useful when you have piles with shallow rock. Say you only have 13 or 14 meters of pile and you have a very high load, compression load on that pile. You may not be able to install reaction piles necessarily that can provide enough uplift, or you might not, it might not be affordable to bring in enough load to really test that pile with a static load test. So that's where the dynamic test can be somewhat useful. Another method that's very common around the world these days is the statnamic test. And that is not quite dynamic and not quite static. So there is a reaction load that in a frame that's brought in and set over the pile. There is a small explosion. Don't be scared. It's very controlled, no problem. And then there's a dampening system. So the load is not immediately applied to the pile. It's applied very quickly, but in a controlled manner based on that explosion and then the reaction of the mass that's inside the reaction system. So it happens very, very quickly, and it could be, again, very economical for very large loads, to test very large loads on piles. But again, it's not direct. So it has to be, there are some correlations that you have to be careful of when you run the test and then try to extract the actual static load that is what you're really looking for in the final design of the pile. And the other method that we're seeing much more in the US finally, because I've been a big fan for a long time, is the bidirectional load test. And that's where, instead of having the load cell at the top of the pile, the load cell is put in the at some point in the pile. Often when we install piles to rock, it's at the bottom of the pile, so that it's testing the actual rock strength and the shaft resistance of the pile. And when we say it's bidirectional, that's what's happening. It's pushing, applying load in both directions from the load cell. And one of the reasons I like it is we can test very high loads, again, without having to install reaction piles or get a large weight sitting up above the ground surface, which is not necessarily always the safest thing to do. And again, we can get a good separation between the toe resistance and the shaft resistance. Now, the only downside is we do need, since it is happening in both directions, you have to make sure that you have enough shaft resistance to react and push get your full toe resistance. If you have very, very short piles, you will start to push this part of the pile out of the ground and really not be able to apply the full load to the bottom of the pile. So again, it's a great system, especially for very, very high loads that you want to test, but you do need to make sure that you have enough resistance in the pile shaft to do it. So non-destructive testing. So after we've actually put the pile in the ground, maybe we've load tested, can we test for the integrity of the pile? Well, the DFI has a guideline specifically for auger cast in place, but you could use it for CFA, same thing, for using non-destructive tests to test integrity. One of our committee members, Bernie Hertline, has also authored a general book on non-destructive testing. That's a great reference. It contains a lot of the same information, and Bernie participated in the development of this document as well. But the most common tests we see, one is the low strain pulse echo test. That is where this is the top of a CFA pile, and you can see the hammer that someone has, and they are going to hit the top of that pile. And there's also a receiver that's placed on the pile top, and you measure the acceleration of the wave through the pile, and then the time that it takes for that wave to return to the top of the pile. Again, this method, because it's dynamic, it's called a low strain dynamic test. It's great for driven piles. We have to be very, very careful of using it for CFA piles sometimes, because it is very sensitive to differences in diameter. And because we're not casing these piles, we often have a little bit of a difference in diameter. So in particular, if you have very soft soils at the top and you have a wider pile at the top, that comes back to a smaller diameter at the bottom where you have stiffer soils that aren't creating as much of a large hole, that can cause some problems with the reflection and the measured wave speed. So those things need to be taken into consideration. And this used to be very, very common. It's gotten a little bit less common because of some of these limitations just for CFA piles. One other common method is downhole sonic logging. So that is a casing is actually put in the pile when it's cast. And then that casing is left open or filled with water actually. And then a tool is put down the casing that has sends a test signal, and then you have a receiver, and all you're doing is measuring the speed that or the time it takes for that signal to get from the source to the receiver, and plotting that velocity with depth. And that velocity with depth can give you some indications of any potential defects in the concrete. It is also sensitive, though, to changes in the surrounding soil stratigraphy. Once you get into very stiff soils, that can change the velocity from very soft soils. And if you have reinforcing steel in the upper part of your pile, that will change the velocity of the wave through your concrete or grout, because now it's going through concrete and steel, as opposed to maybe lower in the pile that's just concrete. So those are just things you want to keep in mind. You don't want to just use the test results directly, but you want to make sure that you understand the stratigraphy that you're testing in and the pile geometry and any reinforcing. Thermal integrity tests are becoming much more prevalent, I think, at least in North America. And these are what they sound like. We measure temperature, and we generally do these by attaching a string that has about 3 temperature gauges per meter, or 3 to 4 per meter, and all the way down the pile. What you can also do is, within the first 24 hours after you cast the pile, you can put a casing in when you cast the pile, and then within that first 24-hour period, lower a probe down all the way through the pile. This is my preferred method because it measures continuously, and you don't have to pick a time to try to run the test. Because what you're looking for is, we're looking at the heat of hydration throughout the column of the pile. And what we're really looking for are differences in the heat of hydration, because those differences in the heat of hydration, and we need to maybe not worry so much about the top and the bottom, because we're getting soil. We either have air on top of our grout column here or soil below our grout column. But within the grout column, we just want to make sure that we're not seeing any really sharp decreases in temperature that would correlate to a soil inclusion where we would not have a full column of grout. Again, it's also not necessarily direct. I mean, the measurement of the temperature is direct, but again, you just want to be aware of the stratigraphy that you're testing it in. And because you are measuring temperature directly, it can give you some very nice results in terms of the predicted diameter. If you know how much grout you placed or concrete you placed in the pile, so you know the overall volume of the pile, you can get a good representation of the average diameter of the pile. Okay, so lateral load tests, I don't really want to get too far into the means and methods. Those are pretty standard, where we have a reaction system of some sort, and we're pushing off of that to apply load to the test pile. And then we're monitoring the movement of the pile head at a couple of different levels. So we're monitoring lateral movement as we apply load to the pile. What I want to say, though, is we generally, and it's just the nature of what we can test, right? We generally are testing one pile, and it's in a free head condition. And geotechnically, at least in a lot of codes, 1 inch or about 2.5 centimeters of deflection, that's considered the ultimate load. So whatever load causes that deflection, we then divide by 2. But the structural engineer will often take that allowable load and apply it to all the piles. The problem is, if you have a large group of piles, that one pile you need to account for the design of that group with the reduction of the allowable load of the piles. And that's really the only thing that I want to point out about that, is we need to be very careful about when we give structural engineers pile capacity, that we're making sure we're telling them it's only for one load or one pile. And I'm going to very quickly go through the automated monitoring system. So we have, again, parameters that we can measure in real time while we're installing these piles. The depth here with time, so it's increasing and then decreasing as we pull the tool out. This is the torque or the fluid pressure driving the tool, and then the grout flow or volume as we're casting the pile. We can also plot those versus depth. So we have penetration rate, withdrawal rate, the fluid pressure, and we can correlate those to tip resistances. So if we have a cone tip resistance of a particular soil, and then we have the torque that we was required to advance the tool and the penetration rate, you can make an estimation of the effort that's required to advance the tool. And that looks a lot like the tip resistance. And what you can do is watch that in real time and sort of make sure you're getting into the appropriate stratigraphy if you have the boring or CPT data available. And again, these are parameters that you can watch both from the operator or inspector in real time as the piles are being cast. So Neil,
Morgan, you'll have to wind up in a couple of minutes.
Okay, and this is actually the last thing. One of the things that's being worked on now is called monitoring while drilling. And it's actually taking these parameters, torque and penetration rate, and estimating capacity of the pile. So again, we have this original effort, this incremental installation effort that's directly related to torque and inversely proportional to penetration rate. But if we take the cumulative, not the sum, but really the integration of this curve versus depth, we can get a relatively accurate representation of the total energy required. So it's like measuring pile driving. The amount of energy required to drive a pile is often correlated to capacity. And we're starting to do the same thing where we're taking the amount of energy required to install the pile, and this final value can be related to pile capacity. So that's that. I've got some additional slides, but those are for another time. But those are really the items that I wanted to cover today. And I appreciate your patience. I know I went a little bit over. So.
Thanks so much, Morgan. Definitely a high-powered presentation from your end.
It's a lot to cover.
Straight away jump to the chat box. If you open the chat box, we'll be taking the queries from the top. We'll be selecting only the important queries to allow all the distribution of the questions. We commence with the observation from Manas Day, the first question. His question is whether CFA piles will be useful for solar plants, the solar panels.
That's interesting because they're often quite short. So we see, and Sunil, you and I were talking before this about helical piles. We often see helical piles being used for these sort of very short foundations for things like solar panels. I mean, theoretically, sure, you could use them, but it may not necessarily be cost efficient, particularly if you're using the hydraulic rigs. Those are very large rigs, and that may be a little bit cost prohibitive for these very short piles. As you develop the technology and you have some of the specialized, those smaller rigs that I showed for low headroom or limited access areas, it may become a little bit more cost efficient. But I would think that some things like hollow bar micropiles, self-drilling, or helical piles might be more efficient for shorter piles.
Solar panels are finding very nowadays intensive use. So I think definitely this technology will be of great use. Next, I take up a question from Thomas Constantus. What is vertical deviation for CFA? How does that compare with deviation from other piles? I believe it should be the same answer. What applies to other is applied to CFA pile also.
Yeah, what's allowable is generally the same. So that's going to be a matter of what's in the specification. So there's usually a specification of what the allowable vertical deviation is. And what is done is those, with the hydraulic rigs that you're using in India especially, those masts have inclinometers. So you can tell that they are vertical, and that's how we maintain the pile verticality within the pile tolerance. Is it's automatically measured, and the operator can adjust that if they need to.
Okay, Venkata has one question. If you come across different strata, whether you'll be changing the grouting speed?
Yeah, that is interesting. So if you have, it's not necessarily, you're not going to be changing the speed that the grout is coming out from the grout pump. That's going to be standard, or it's going to be set. What you may change is the rate at which the operator pulls the tool. So if you know that you're in a very stiff strata and the hole is going to be very close to the diameter of the tool, you may not want to pump much grout. So you may want to calculate a rate of extraction that places a certain amount of grout. But as you get closer to the ground surface and maybe the soils are softer, you could say, okay, we want to place a slightly more grout. So we're going to slow the tool extraction down in the upper, say 5 meters, because we know the ground is very soft, and we're going to continue to pull, but just at a slower rate so that we have a higher target of grout supply in the upper portion of the pile.
That's nice. Manish Kumar has an important question. Can we tackle presence of occasional boulders?
No, that's a problem for almost all the pile types. So for driven piles and CFA piles, that is a problem with boulders. We will often, if we get into situations like that, we have to have conversations with the owners and structural engineers at the beginning of the project and say, it's very likely we're going to hit a boulder or two on this job site. So when we do that, we're going to just pump that pile, but we're not going to use it. We're going to all have to agree to add a pile. And because the system is so fast, that can still be a more efficient way. But if you hit a boulder with an auger cast pile directly or CFA pile, it's just going to stop. You're not going to drill through it. So if you have a lot of boulders, maybe you want to think about micropiles or drilled shafts, but the occasional boulder is usually we just abandon that pile and put another pile within that group.
A proper mapping will be very useful, because if we encounter boulder, that will put our whole plan into jeopardy.
Yeah.
So yeah. So then I would put the next question from Constance, that what encounter if liquefiable layer is encountered. I think while you are executing CFA pile, it will be plain sandy layer. So it will be a usual method to be going.
Yeah, there's no limitation, or there's no issue with installing the pile. Those liquefiable sands are just something that you're going to want to keep in mind during the development of the reinforcing steel. So you're going to want to reinforce the pile and consider that loss of resistance when you're doing your lateral analysis. But there's we install CFA piles in liquefiable soils on a regular basis.
Manas says again a good question. Are you going to change the auger geometry and design if you come across cohesive and sandy soil? More important is auger geometry. Are you going to change auger type if you are going to encounter sandy or cohesive soil?
We will. Yes, we if we know that we're in a predominantly sandy soil, we will use what's called the typical, or that what I showed was the pingo bit. If we're in a clay soil, we will use that flat blade clay bit. But oftentimes we have both. I mean, that's just we have some clay over some sand or something like that. And in that case, you're not going to change diameter, or sorry, you're not going to change the tool in the middle of the pile. You're just going to pick a tool that's sort of in between and can do both. So we have some general tools for soil when we have mixed soils as well. But yes, you will tailor often the cutting head to the soils that you are expecting to encounter.
If you scroll down, Tenny has a good observation and important observation he has to say. I would like to read it for a general benefit of the audience. Firstly, thank you for your clear and essential exposition on the CFA design criteria and practice. also to the site references. Apart from comparing other piling methods, CFA in some way in competition with jet grouting. The obvious advantage of CFA is the rate of installation, which is far more superior than the jet grouting. Secondly, application of the grout of concrete flow and the pressure monitoring system, which controls the rate of extraction of the auger from pile, has greatly improved the CFA technology with respect to what it used to be earlier. So less concrete or grout wastage and sharp bulging makes an improved foundation product. So any comment on that? Martin?
Yeah, the automated monitoring that we're able to do these days has been a big change in the last, say, 10 to 15 years in the US. We, for a long time, were not allowed to use auger cast piles in the United States for bridges, for example, because they just didn't feel like we could control the quality of the flow enough or we could at least monitor and guarantee the quality of the pile to a level that the government wanted them to. But now you have a lot more control over just sort of guessing where the grout is being placed with these automated monitoring systems, and you can really verify and control how the piles are cast and cast correctly.
Right. Manish Kumar again has a common concern, which most of us are sharing. You install a bidirectional cell, then there are several strain gauges fabricated into the cage, and then you push the cage. So how would you do that without damaging or without any?
We do it right after the pile is cast, so the pile is still in a very fluid state, and we personally are about to go on Monday and install some relatively large diameter piles that are fairly deep, and it's a concern, but it's with the grout. Again, I mentioned those additives that we have now. There are fluidifiers and water reducers where we can, again, keep the grout in a very flowable state long enough that we can install whatever reinforcing steel, or in this case, lower the load cell. And I'm not going to lie, though, that's for a long time, bidirectional cells were only used in drilled shafts where they could place it in the shaft before the concrete was placed. But as grout mixes and concrete mixes have improved over the last 15 years with these additives, that's really started to speed up our use of bidirectional tests for auger cast and CFA.
Actually, bidirectional cell is going to retard. It is going to offer more resistance to the cage, which is otherwise also is a big problem.
It does have, it's got a hole in the middle. It does allow, it's not perfectly solid, and it is a pretty good bit smaller. So if you're using a certain diameter pile, the cell won't be that size. It will be a good bit smaller. So that is a problem that the makers of bidirectional load cells recognized and have worked very hard, because they want to use their equipment in the CFA pile market.
Ramanaj Das, I'll come to his question. What should be the minimum spacing of the pile to get a vertical group efficiency of unity? I think that this is applicable to all the pile in general.
Yeah, the general effective or the general consensus seems to be that if you have 3 diameters, and that's center to center, so that's not the clear spacing between the edge of the pile, but from center of pile to center of pile, if you have 3 times the pile diameter, you shouldn't have to worry about reductions for group effects. So any closer than that, though, and you do need to start worrying about, you're not going to get the same group capacity as the sum of the individual piles. But as long as you keep 3 diameters as a minimum spacing, generally it's agreed that at that point you should be able to use the full capacity of the piles.
Yeah, Mary Ellen, as usual, she is graceful in accepting a nice presentation from your side and a good coordination. Thank you, Mary.
It's always nice to have a friend in the audience to say nice things about you. So
yeah, Venu Gopal has a question. Is the reinforcement in CFA pile will be required up to the toe level? This is a very, very relevant question.
Yeah, and that's a big difference between drilled shafts, which generally have reinforcing all the way through if you do a lateral analysis, and we'll forget about seismic loads for a minute, those are different. But if you're just looking at structural loads from the building, those are typically resolved in the upper, I was going to say 25 feet, so 6, 7, 8 meters of the pile. So if you're doing a 30-meter pile, you do not need the cage to go from a structural standpoint all the way down the full length of that pile. And that's one of the things that makes it an efficient system, is we generally only put the reinforcing steel into the depth that it really needs to. Center bars very often go the full length of the pile, but they're very thin and you don't really have much of a problem installing those.
In India, we are trying to correlate torque with the pile termination. So the next question is relevant from Shivraman. Any correlation between the torque measured during the CFA drilling along the pile length and the pile capacity?
And that's what I was just had enough time to touch on. We are I'd say at the beginning stages of measuring torque, but it's not just torque. I think you should measure torque, penetration resistance, and possibly even rotations, but at least torque and penetration resistance. And yes, you can develop correlations, but we're just starting to develop those correlations in the United States. But that's with these hydraulic systems that you have in India, all measuring those parameters is a standard part of their systems. So you're going to have that data available, and it's great because you should be able to collect a lot of data in terms of the torque and the penetration rate that you used and the capacity of those piles. And you should be able to build a database from that to see what the correlations look like.
In fact, in India also, we have a documented method where torque and the pile termination are correlated. Still a gray area, but definitely we are marching forward in establishing and authenticating this system of pile termination. So there are heaps of accolades being given to you. Dr. Ramakrishna, our ex-chairman of DFI, is also appreciative of a good presentation. Manas is really saying it's a power-packed presentation. Then Heep Huang has a question. What is a recommended slump you would say for CFA pile?
That's a great question. We don't use the slump because the grout or concrete is so fluid that you're not really going to be used as a slump. So I might have had a picture in there, but if you look at the DFI pile manual, there's an augercast pile manual that talks about the flow cone. And I think it's in one of the slides that generally if you're using grout, I think with a standard flow cone, you want to have a flow between 10 and 25 seconds. The problem is, however, a lot of these additives that we're talking about, fluidifiers and water reducers, they increase the viscosity of the grout. So the flow cone is starting to work not so well as we're using more of these additives. So we're using what's called the spread test, which there is an ASTM standard that I think is on one of the slides where you place a large board with a large flat area and you're using the cone, but you turn it upside down and then you pull the cone out and you monitor actually the amount of spread of the grout or concrete as opposed to the slump of the grout. And that's what I would say you would probably want to look at, is either the flow cone or the spread test.
In fact, during our trials at India, the temperature soared to about 45 degrees Celsius. And during that time, we had used a flow index excess of 750 mm. So that was quite a high flow value. Yeah, we did use that. And the temperature was quite high over there. And we could succeed by inserting the cage in that kind of concrete. One question, there are last two questions I'll be taking up. Yadav Rao has a question. Compared to normal pile concreting, what should be the cementitious content for CFA pile concrete?
That's a good question, and I would have to get back to you on actual material content. But why don't I'm going to look for a slide while we go on to that next question that I saw, if you don't mind, because I think we could come back to that question.
Okay. One question, how do you maintain the stability of the drilling hole in a weak and collapsible soil? This is from Thomas Constantus. Can a casing or other method be implemented? Casing is an important thing because one of the projects required use of casing along with the CFA pile. That was an inquiry we received in India. So, question from top. Yeah.
So the short answer is yes, there are certain tools that have a double rotary. And so you're rotating the tool, but you're also in the reverse direction. You have a separate rotary head that can rotate casing into the ground. I do not find that that is very necessary. The intention of either the augercast or CFA is to drill at a speed where you keep the auger flights, you're almost screwing the tool into the ground. You really shouldn't see much soil coming out of the ground until you start pulling the tool out of the ground and pumping the pile full of concrete or grout. And in that way, the auger flights are full of soil. And so if you think about that, you're not just creating a void in the ground. You have a tool that's filled with soil that keeps the hole stable. And then that's one of the reasons that we pump grout or concrete above the tip and create some amount, maybe a meter or two worth of grout concrete over the tip of the tool. Is as we start pulling the pile out of the ground and creating the void, we already have a grout column or concrete column that's being created, and that stabilizes the hole. So even if you have collapsible soils, if you cast and place the concrete right, that concrete head pressure is going to be much higher than any of the vertical effective stress of the soil because of the unit weight of concrete is going to be higher. And so it should not allow for any soil to collapse into the fresh column of the grout.
Nice one. A final question, let me take up the factor of safety to be considered in CFA pile design for end bearing and skin friction. He is talking of separate partial factor of safety for end bearing and skin friction.
Yeah, that is a great question because it's a question of, now that we especially have all of these parameters that we can measure in real time, should we be allowed to reduce it? The basics, we in general never use a factor of safety of less than 2, and that's when we do a load test. Yes. That's just general practice by code here in the United States. Again, I think you're going to see, as we are getting better records, that maybe that factor of safety starts to go down because we don't have the uncertainty in every pile. We have these great records, but that has not happened yet. And I don't think will happen for some time. If you don't have a load test for lightly loaded piles, we often use a factor of safety of 3 and then show that by calculation, we have a much higher capacity than the load on the pile, but that is very uncommon and typically only used for light compression or uplift loads.
Thank you very much. I'll have to put up the end to this question answer session. There are a couple of questions from Gustav as well as Karthikeyan. I'll beg pardon because we are oozing out of the time by about half an hour.
I know.
Thank you very much for to the audience for putting up a very, very interesting questions. And yes, I'll steal some of the appreciative words from the audience for Morgan, and that will be, it's a power-packed presentation. To put it in just a couple of words, it's a power-packed presentation. Thanks a lot for a very wonderful presentation. I think this is a beginning of a learning base for a CFA pile, or what we call the agar cast in situ pile. And very, very happy and really privileged, every one of us over here, to have an expert and learned person like Morgan NeSmith addressing to the Indian audience who are keen to see that CFA pile finds light of the day in India. That's it from my side. As a moderator, I'll pass on my this platform to the organizer, namely the Pranav, to take over.
Thank you so much, Mr. Morgan and Sunil sir. Mr. Morgan, you wanted to present something at the end. You still want to present it?
Oh, no. I was going to say, I promise you, I will send you a standard mix that shows you the cement content for the grout though. So to answer that one last question.
Thank you so much, Mr. Morgan. Thank you so much, Dr. Sunil Basarkar, for always being there at DFI of India service. And this marks the end of Groundwork 2022 webinar series. And like past 2 years, we'll be again back with Groundwork 2023 webinar series starting January 2023. So stay tuned for more informative sessions and follow DFI India on LinkedIn, YouTube to get updates about the future programs. I thank all the attendees and we'll see you in the future DFI programs. Thank you so much, everyone.
Bye.
Thank you very much. Thanks a lot.
Thank you.
Thank you very much.